Okay, welcome everybody. Today our speaker is José Antonio de Diego Onsurbe, that is visiting us in the ILC with this kind of grants of the Talento Tricontinental. So he has been here for several months. And well, probably most of you know because he regularly visits us. And in fact, he made his PhD here in La Universidad de La Laguna, I think in 1995. 1994, so. And later he moves to the Instituto de Astronomía in la UNAM in Mexico, where he has developed his career. He's mainly interested in extragalactic physics, in particular in a cluster of galaxies and in AGNs. And today he's going to speak about the microvariability in quasars. So please, when you want.
Okay, thank you for coming here. I'm not going to the south yet, some of you. So I will talk about the microvariability detection in quasars as an astrophysical, astrostatistical problem. So I will concentrate on the statistical test to detect variability. But first, let me show you the AGN model, the standard model, let's say, where we have an accretion disk and a broadline region and narrow line region and some jet in some objects at least. And the part that we are interested in is the part that emits in the optical light. So it's the accretion disk and some part of the jet, which is between 1 parsec and 10 parsecs approximately. And this is important because this, the part that we will study here is the microvariability in this region, which is important because it gives us the information about the inner region of the AGNs. And this is the only way that we have to test the structure and the physics in this part of the object. And this is done in the optical with CCD differential photometry. And the thing is that we have observations in the telescope, and we see the light curve of the quasar, and usually a control object, which is a star in the field. And we see that the quasar may vary at some point. But the problem is that in normal quasars, the variation is small. If we see, for example, a BL-like object, they are very variable, and we see variations of about 1/10 of a magnitude. But in quasars, usually the microvariability is about 1/100 of a magnitude. And the fact that this variability is comparable to the photometric errors makes the things a little problematic. So there have been a lot of tests that have been proposed to study this. The first by Howell in 1988, who used the F-test, and he made a very, very complete study of the CCD noise, the flat fields, the bias, the difference between the stars that were compared. The F-test basically means that you have the light curve, you measure the standard deviation of the light curve and compare with a reference star. Lately, Young and Miller and Romero and Celon invented what is called the C-test, which is basically using the standard deviation instead of the variance as in the F-test. I will talk a little about this C-test, but it has many problems. By the same time, in 1988, I proposed to study these objects with my collaborators using the one-way ANOVA, Analysis of Variance. Later, 4 years ago, I made a study comparing several tests, the chi-square test, the C-test, the F-test, and the analysis of variance. And in this work, I showed that the chi-square test is not reliable because you have to know all the sources of error in your data. The C-test is not really a statistical test. The F-test and ANOVA work well. They are reliable, but ANOVA has a lot of more power than the C-test, than the F-test. And with more power, I mean that you can find smaller variations. From here, people started to abandon the C-test, which was very popular before. It's still used, but people started to move to the F-test, which is simpler than ANOVA. José proposed some kind of a scale test, which is basically the same that proposed Howell, but simplified, because the problem with Howell treatment is that it was a little complicated. Then José and Hugh and Chan and others have started to use which is called multi-testing. Multi-testing is used, for example, in genetics, and you compare several things with different tests, and you have to control that you have not a lot of type 1 errors. And this is done in the simplest form with Bonferroni's correction, but there are others. These guys made this multi-testing using which I call the double positive test. It means that they use two tests, and they say, okay, the object varies only if the two tests reject the null hypothesis. The null hypothesis in this case is non-variability. If they reject that they are not non-variable, then they accept that they are variable. But this multi-testing has problems that we'll show you later. And what I have done in this year is make a study of how to include several comparison stars in the analysis. And this has been done in a paper which has been accepted now in the Astronomical Journal, and another paper that we are preparing with my collaborators here. But why is so important to the statistical methodology? Well, the first thing is that the different tests have different strengths and weaknesses, and you have to know about this. And they are more or less appropriate depending on the characteristics of the data sets and the population, the parent population that you are studying. And all the tests rely on a number of assumptions and conditions, such as independence of how you obtain the data, Gaussianity, a minimum number of data points in your analysis. And poor understanding of these test capabilities and the possible violations of the conditions may jeopardize your study. So this is the importance of making a good statistical methodology. And this can be studied using the power analysis. I will explain very briefly which is power. In a test, you usually have a null hypothesis, which is this, which basically in our case is that the quasars are not variable, so you expect that the variability is 0. And you have the real wall. The real wall is that the quasars may vary and have a variation which is not 0, and this is the effect size. Then for the null hypothesis, you have the type 1 errors, which is the significance of your test, that usually is about 1% or 0.1% or whatever you want. The type 2 errors, which is beta, and the power, which is 1 minus beta. All this on here. And power, this power depends on the level of significance of the test. If your level of significance is here, then the power is larger, or if it's here, it's lesser. The sample size, well, in this case is a Gaussian, which is the simplest form of view the power, and the Gaussian has infinite number of data. But for tests like a t-test or the distribution, the shape of the curves changes. So the level of significance, the sample size, and the effect size will define which is your power, and it's being calculated usually through the non-central distributions of the F distribution or the T distribution. So how to study power? Well, if you have a parametric distribution like the F distribution, you can do it analytically. And if you have any distribution, which be parametric or non-parametric, doesn't matter, you always can rely on Monte-Carlo simulations. Okay. Let me start with simulations and see what happens. This is a simulation of 35 data points with an amplitude of 0.04 magnitudes of variations are here. And this is a comparison star or a control star. If you study this by ANOVA, you make groups of 5 observations, for example, and you have this light curve, which shows the variation very clearly. And, well, in the case of ANOVA, the only trick is that the frequency that you are observing is much larger, or less time, than the typical variation. So these are the simulations, basically. And the analytical power, I will not enter into mathematics, but this can be calculated, and there are programs like the R language, you can calculate it directly, or MATLAB. You can calculate which is the power for the F test, for the F distribution, or for the ANOVA. ANOVA has groups of, in this case, of 7 groups. So you have 7 steps. And the first group is at 14, at 21, and so on. Multiples of 7. And this is the power for variations like I showed before, the 0.04 magnitudes. And you see that from 21 observations, you get that the ANOVA has a lot more power than the F-test. But I said that the power also depends on the effect size. If you descend these variations to a half, 0.02 magnitude, the F-test is basically doesn't find anything, and the ANOVA you still have some power to low number of observations. This is analytically, but what happens when you compare this with simulations? Well, you have that the ANOVA, analytically and simulations agree very well, but the F-test, the analytical is larger, the power, than the actual power you have in the simulations. So what happens here? And what happens is that the F-test requires that your data is normally distributed. And if it's not normally distributed, you lose power. You have more type 2 errors that you expected. And this was shown by Box in 1953. And in this case, it's very simple because we have a bimodal distribution. The object doesn't vary here and doesn't vary here and only varies here, but it's all the errors are Gaussian, so you have 2 Gaussians. But 2 Gaussians is not one Gaussian. So it's a bimodal distribution, so you have not a Gaussian distribution, a normal distribution, and you have this loss of power. Another important thing is that the reliability of your test. And this means, well, how confident can you be on the results of your test? And you can measure several ways, but for example, with the likelihood or the false discovery rate, likelihood is the power of your test compared to the number of type 1 errors that you have. And the first discovery rate is the type 1 errors that you have, or the significance level of the test, compared to the number of the null hypothesis rejections, which is basically the same type 1 errors plus the power of your test. And what you see is that the higher the power you have, the higher the likelihood, and the smaller the false discovery rate. And you have here some samples, for example, for the F-test and ANOVA. You have that the power, for example, to 1% is 64 and 74, and your likelihood is 74 and 64, and the false discovery rate is 0.133 and 0.154. So what does it mean? What this means is that if you have a test with a lower power, it's more probable that your fraction of false discoveries, of false rejections, than if you have a test with more power. So you want to have not only more power because you will detect more, but also because your detections will be more reliable than with low power. And here I will compare this with the techniques that other guys use in the study of microvariability, and particularly these double positive tests, which means that variability should be discounted by two tests. This was done by José, Hugh, and Chand, and usually they use either two F-tests with different comparison stars in the field, or one F-test and one C-test with the same comparison stars. The problem here is that the results of this test, if you are using the same data sets, are correlated. For example, in the simulations, if I use the analysis of variance and the F-test, this is logarithmic scales, you see that the correlation is clear, no? If you use the C-test and the F-test, like some authors, you see this strange correlation. The shape of the curves depends on how many points you have in your light curves. And well, you see that there is a strong correlation between the C-test and the F-test, because basically this is the square root of this. So, and if you compare to F-test, well, the correlation is more or less perfect. Here I used two comparison stars with the same brightness and the same errors, so the correlation is quite clear, no? But if you see here, for example, and you say, okay, let's take a little zone here, and you will see if you make the study that the data is more or less normally distributed around the correlation point. So if you have, if you study two tests, if you are using two tests, you have correlated results, and you can express, or you could express if you know, but you don't know really, the result of one test as the probability of having the result in the other test. So, but you don't know which is the relation. Here you know because our simulations, and I made 1,000 simulations, I can calculate it. But usually you have only one light curve, and you cannot make this study. But you know that they are correlated, and you don't know how they are correlated, so you cannot measure which is the probability of finding that the test give you both double positive, or one positive and the other negative, or both negatives. And the other thing is that you can see this here, this -3 and -3 are the, let's say, the 3 sigma level of detection. you see that the test with the lower power biases all your results. In this case, the C-test only detects these two objects. The F-test detects all the objects here. But if you use a double positive test, you will only say that two quasars are varied here. And in fact, if you see the study by Hu et al. For this Diller-like object, they find 6 dubious events, and all the dubious events, it's the C-test which fails to reject the null hypothesis. So this double positive test is not the best way to study microvariability. But you may think that you can use more stars in the field to get a better estimation of your variability, of the variability of the quasar. Basically, this is done in this equation, which I will not enter which does it means, but basically it says if you can weight the errors for the stars, so they are all at the same level as the quasar, you can have a larger data set of comparison stars than only one star. So here we have for one single star, which is the usual way that the F-test is done, and 2 stars. And you see that the critical number is lower for 2 stars. And when you make well, this is for non-variable, so the control star fits perfectly the null hypothesis distribution. But when you go to a variable star, well, you see that you have a lot more of objects that you detect the variations. And you have here the numbers. For 3,000 light course simulations, at 1%, the level of significance of 1%, you expect about 30 type 1 errors, which you have in all the cases, for one star, for the other star, or for this stacked 2 stars. And for the variable, you find 1,900, let's say, detections, so if you are using only 1 star, these 2, or more than 2,000 if you are using 2 stars. So this stacked or this enhanced test has more power than the single F-test. In fact, with 2 stars, you have the same power like in the ANOVA with 1 star. How you measure this? Well, you can use, for example, Joshé's approach or Hubble approach. But we are and this is what I have been doing here during these months, is to find an empirical law, let's say. And you have these stars in the field. These are too noisy. You probably don't exclude them from the fit. And you make a fit which is like a power, an exponential function. And you find this fit, which is correct. You can extend it even to the part that was not considered in the fit, and it's okay. You normalize the distributions. I mean, all points here are as a complete light curve. It's about 60 observations. You can normalize it, and you can, if you normalize this, for example, for this star here, you get this. And this is a cuckoo plot, and you see that it follows well the straight line, which is the normal distribution, and you can convert these magnitudes to the magnitudes of at the point at the magnitude of the quasar, and you get this. The shape is the same if you see this is the same as here, but now the data is transformed to the magnitude of the quasar. And you can do this for all the stars here, and you have a better estimation of the error at the quasar. This is with the F-test. But what if you want to use ANOVA? This is not in the paper. This will be in the next paper. And in ANOVA, what you will do is use a balanced nested design. And nested design means that you have, for example, 3 groups of observations. Each group has 5 images or 5 observations. And you have, for example, 3 comparison stars that you will compare. And one comparison star means a different test, let's say. And then you have, well, you can calculate the number of degrees of freedom. You can compare the expected mean squares, which is a measure of how, which is the square of the dispersion of this data with respect to the mean of the test, or the mean of the observations, and the mean of the group. And without entering into the mathematics, but you see that there's a square for the groups, that is what we are interested in, depends on the real dispersion or real variance of the groups, plus the dispersion of the single observations, and the dispersion due to the tests. So we can compare, if we consider this is 0, it's not varying, we compare this with these other values and see if and test if the object is varying or not. Basically, this is the method behind using the balanced nested design. Here we have a simulation. This is the varying quasar. This is a control star. And what we have is this. This is the enhanced F-test, the curve of the enhanced F-test, number of detections against the number of bright stars in the field. This is for the nested design, this curve of circles and solid line. And what we have here, well, first, notice that this star in the star number 2 and this star in the star number 1. Because to make the enhanced F-test, you still need a reference star. And you don't need this for the ANOVA, because the ANOVA uses all the stars as reference stars. So you have 1 star more. And here you see that with 2 stars, well, in reality 3 stars, because you need the reference star, you have the same power more or less like ANOVA with 1 star. But ANOVA is always over the power of ANOVA is always larger. But these 2 curves are considering the same errors, either using Yoshi's transformation, Howell's transformation, or the transformation that we are applying with in Jana. What if you don't make any transformation? Well, precisely the nested design is able to deal with this, and it's this curve here. It gets almost the same power of the curve with the same errors. It's slightly less because, well, when you put another source of variation, you get some power. But you don't lose a lot of power, and it's over the enhanced F-test. So this test is quite powerful. And here you have the number of type 1 errors. As I am considering the same quasar dataset light curves, they are strongly correlated, all the errors, but you see that you expected around 10 type 1 errors. It's more or less, it's by there. No? So conclusions is that we have studied analytically the F and the analysis of variance test. And we have seen that the F test has problems with non-normality. We have studied what happens when you use several stars or several tests. And arrived to the conclusion that double positive tests are not good procedures to study microvariability. But the enhanced F test and the nested ANOVA designs are reliable and very powerful. And yes, well, then use power analysis and simulations to compare methodologies is a strong tool to make any study. And these results, when applied to real data, can improve the future studies and help to understand the physics, physical mechanisms that are responsible of AGN phenomenon. And that's all. Thank you.
Thank you very much for your talk. So now we have some time for questions.
So could you expand a little bit more on how this microvariability can tell us something about the physical mechanism of the AGN? I mean, what are the expectations? Or
what are the
I mean, what do you expect to get? I mean, when you get some variability of any kind, with some certainty, what can you learn?
Okay. Let's go to the, I think it was the first or the second. Yeah. We are studying the optical region, so our variability should come from either from the accretion disk or from this part of the jet. And one of the things that we have been done is comparing radio-loud quasars and radio-quiet quasars. And you expected that in radio-loud quasars you had stronger variations. The variations come from the jet, and this didn't happen. We found that they have basically the same variations. So it's possible that at least part of the variations come from the accretion disk. And the mechanisms are very different, because in the accretion disk you may have variations because, for example, hot spots in the disk that are rotating, or you can have some fall of material into the black hole, or you can have a disturbance because another body or star, whatever enters in or affects the accretion rate of the black hole. But if you have variations here, you basically have shocks, and this is totally different. Shocks because they are having material ejected from the center of the AGN, no? And this could be done also because you have a large increase in the accretion rate, for example, or whatever, or disruption of a small object or whatever in the accretion disk. But the thing is that they should have different signatures. If you have a variation in the accretion disk, which is basically a thermal origin for the radiation, you expect a thermal variation. And if you have variation in the jet, you expect a non-thermal variation, which is synchrotron variation or something like this. So studying colors of these variations is also important.
But I mean, you said that in the end, I understand that the so more precise that you can go in terms of variability characterization. You said that you are typically going to 0.01 magnitude or so. So closer you can go to the central parison, right? Or so there is a connection between your accuracy and the center position.
Okay, the position is given, let's say, by the time scale of the variation, because of causality reasons. If you have minutes in your time scales, you expect a variation which is in the in a source that is more or less like the planetary system. But if you have variations which is in months or years, then you have variations that, for example, 1 parsec or 10 parsecs of distance, several years of variability. And you find variability in all the time scales. If you study BL lags, even more. However, if you have a shock, you may have small variations in this part too, because you have strong changes in the magnetic field, and so on. So you have to study. If you measure microvariability is a small amplitude, because it's that, and fast variations in time of hours, let's say, minutes or hours. It can come from the question disk, either, or from the jet. You don't know. You have to study in colors also to know that, and it's not clear by now.
Sorry for being insisting so much, but I know you were living in you were having access to data where you can explore variability of the order of 1,000 magnitude, whatever. It's the 100 that you're measuring so far.
100 is what you can get in a normal telescope.
Okay, but imagine that you can go to 1,000 with a special design telescope or whatever. That will tell us something different?
Well, if you can, it depends. For example, let's say that you can measure with a large telescope. Then you can go to smaller times. When we study this, we study about minutes. Every observation was around 1 minute, every single observation. We could do that in a fraction of a minute if you have a larger telescope. But if you expect that the size of your variation is smaller when you go to smaller time scales, then you need a very high signal to noise. What happens also is that you have limited, not only because of the amount of light that you have, which is the strongest limitation, but you have limits also because, for example, which is the accuracy of your flat field or your bias or whatever. So it's difficult to get much lower than 100th of a magnitude.
Okay, any more questions? So, well, if there is no more questions, so let's thank again to José Antonio for his talk. So.